Hey everyone, and welcome to The Explainer. Today, we're taking a really fascinating journey through the world of mathematics, specifically diving into the Cambridge IGCSE Math 0580 syllabus. And we're going to bridge a pretty incredible gap today. We'll be starting way back with some brilliant 17th century mathematical breakthroughs, and then connecting them directly to the modern advanced algebraic tools that you absolutely need to master. Whether you're graphing complex curves or untangling tricky logarithms, it all starts right here. Let's get into it. Okay, so here's our roadmap for today. We're going to kick things off with the architects of modern math, then move straight into coordinate geometry. From there, we'll tackle graphing quadratics and cubics, break down composite and inverse functions, and finally cap the whole thing off with exponents and logarithms. Now, before we can plot a single point on a graph, we really need to understand where the graph actually came from. So let's travel back in time to the middle of the 17th century in France, which was an absolute golden era for mathematical discovery. Take a look at the philosopher René Descartes. You've probably heard him famously ask, "How and what do I know?" But mathematically speaking, his true genius was realizing that algebra and geometry didn't have to live in separate boxes. By linking them together, he quite literally changed modern scientific thought forever. What's really interesting about this slide is how these three contemporaries essentially built the mathematical world we live in today. Descartes gave us Cartesian coordinates, which, no surprise, aren't named after him. Then you have Blaise Pascal, an absolute prodigy who was proving major geometric theorems at just 16 years old and helping found probability theory. And finally, Pierre de Fermat, who basically invented number theory and was arguably Isaac Newton's equal. Together, these guys laid the foundation for everything we're about to look at. Actually, speaking of Fermat, I've got to share this wild piece of trivia. Fermat's last theorem, which builds right off the classic Pythagoras' theorem, was a puzzle he claimed to have totally solved, but never bothered to fully write down. That puzzle was so insanely complex, it stumped the world for over 300 years. It was literally only proven in 1995 by the English mathematician Andrew Wiles. It just goes to show how enduring these 17th century concepts really are. All right, let's shift gears to Section 2, Coordinate Geometry Essentials. Let's see how all this rich history builds into the absolute core of your mathematical toolkit. Think of Cartesian coordinates like putting on a VR headset. Just like VR helps us see and interact with entirely digital worlds, the Cartesian plane is the lens that allows us to actually visualize mathematical relationships. Without this system, algebra is just, well, numbers stuck on a page. But with it, algebra becomes visible space, lines, and shapes. It's a real game changer. So, here is your foundational checklist. To really crush this syllabus, you need to be super confident in finding the gradient of a straight line, calculating the exact length and midpoint of a line segment, and seamlessly putting together the equation y equals mx plus c. You also need to know exactly how to handle parallel and perpendicular gradients. Listen, these aren't just random formulas to memorize. They are the fundamental tools you'll be reaching for over and over again. And once you've completely mastered those straight lines, it is time to tackle the curves. Section 3 is all about graphing quadratics and cubics, which is a really fantastic step up in complexity. Let's look at an actual assessment challenge straight from our sources. Say a quadratic has zeros, or roots, at x equals -4 and x equals 2, and it passes through the point -3, -15. How do you find its equation? Well, this is exactly where you apply your toolkit. You know the roots give you the main factors of your equation, and that single coordinate point, that's the secret key you substitute in to find your stretch factor, a. And you know what? We can push this logic even further into cubic functions. The crucial point here is leveraging the specific information you're given. If you have the zeros, you have your building blocks. By substituting the given values for a and d along with those x-intercepts, you can set up simultaneous equations to unlock the missing coefficients b and c. I'm telling you, it is incredibly satisfying when those puzzle pieces finally click into place. Now, as we draw these more complex curves, we have to talk about boundaries, specifically asymptotes. These are those invisible lines that a curve approaches, getting infinitely closer and closer, but never, ever actually touching. When you're sketching graphs of inverse proportions, like y equals 1 over x, you absolutely must be able to identify and write out the exact equations for these asymptotic lines. All right, moving right along to Section 4. We're going to step back from graphing for a second and dive into the heavier algebra of manipulating functions themselves, composite and inverse functions. I like to think of a composite function as a mathematical assembly line. You start with a raw input and push it through your very first machine, function g. But the output of that machine doesn't just sit around, it immediately becomes the raw material, the new input, for your second machine, function f. Let's walk through it together. Say your f of x is 2x minus 5, and your g of x is x plus 1. How on earth do we find f of g of 0? Well, you always start from the inside out. First, we solve that inner function, g of 0, which is simply 0 plus 1, giving us 1. Next, you take that 1 and you drop it straight into the outer function. So f of 1 becomes 2 times 1 minus 5, which gives us a final answer of negative 3. See, it brilliantly illustrates how breaking down a scary-looking notation into bite-sized sequential steps makes it totally manageable. But hey, here is a massive warning sign. The order of operations is literally everything here. F of g of x is almost never the same as g of f of x. If you swap the order of the assembly line, you build a completely different product. By mapping out these functions, you can clearly see why changing the order completely alters the resulting algebraic expression. Don't fall into that trap. Now, what if you need to throw that machine into reverse? Finding the inverse of a function, like this one right here, is a fantastic test of your algebra skills. You have to swap your x and y variables and systematically solve it to get y all by itself again. You're basically untangling a mathematical knot step by step. Which brings us to our fifth and final stop, diving into the absolute most advanced material in this part of the syllabus, exponents and logarithms. Up until now, our unknown variables have mostly been living on the ground level, right? But consider this equation. 2 to the power of x minus 4 equals 20. The unknown x is trapped way up high in the exponent, and since 20 isn't a neat, easy power of 2, standard algebraic factoring isn't going to help us here. We need a very specific tool to bring that exponent down. And that tool, my friends, is the logarithm. By taking the log of both sides, we can literally pull those exponents down to our level. But to pull that off, you've got to know how to manipulate the logs themselves, like the pretty complex expression we're looking at right now. Mastering these rules, knowing how to add, subtract, and isolate logarithmic terms, is the ultimate key to unlocking those really top-tier assessment questions. Wow, we have covered some seriously incredible ground today. We started with Descartes drawing the very first Cartesian planes over 400 years ago and worked our way all the way up to manipulating inverse functions and solving complex logarithms. Ultimately, mathematics is just a language we use to describe reality. So my final question to you is this. Now that you're armed with this powerful mathematical toolkit, how will you use it to model and understand the world around you? Keep practicing, stay curious, and thanks so much for joining me on this explainer.